existence and uniqueness of solutions of nonlinear differential equations. And there's a number of conditions that you have to start placing on your equations in order to get them to have solutions that exist and are unique. And then, so basically what where the point that we're at is that the last thing we said is the idea of when you can get a unique solution that exists for some time, but it may not be very long. So then the next question is, well, that's not really what we would like in general for engineering, to not have solutions that exist very long. So then we want to say, what are the conditions they need in order for the solution to exist and be unique for all time, essentially. Yeah. So we also talked about this idea of Lipschitz continuity, which probably won't make too much sense, even though I think you've seen that in the papers.
Yeah.
So then it probably won't make too much sense what I'm saying until you watch that thing. But then once you do, then this also should clarify in the papers, whenever you read any of the papers, and we always make an assumption that when we work with, so in any of our papers, oh no, this is not the right one. In any of our papers where we have system, so far in our papers we've worked with systems of nonlinear ordinary differential equations, and I guess let me preface this before I keep going to show how this is related to stuff we're learning, to anything. So in the research group, and in my PhD, which my PhD was not that long ago, so what I learned in my PhD is very similar to what we're doing so far, even though we're branching out now. But, so in all my PhD, these are the systems I always work with. Systems of ordinary differential equations that can be nonlinear. And the reason for this is that we know that many chemical process models that we learn as undergraduates, like the CSTR model and stuff like that, they are described by systems of nonlinear ordinary differential equations, so it makes a lot of sense. It also turns out that, like, when you discretize a PDE, a lot of times you can also get it to the discretization will be a system of ordinary differential equations. And so it makes a lot of sense to work with systems of ordinary differential equations. Something that we're trying to move toward now in the research group is moving to systems of partial differential equations and trying to look at, okay, what is the theory that's relevant there and what goes on. But we haven't really done that yet. So we're working on it. Enrique's pioneering. Yeah! And soon we will have some other people pioneering as well. So basically, if you look at any of the papers that have come from this research group or that I've done in my PhD, they'll have systems of this type. In every paper, we make an assumption that the right-hand side of this differential equation is locally Lipschitz. And the reason that we do that is related to these issues of existence and uniqueness, that essentially we're trying to place some, as minimal assumptions on the right-hand sides in order to make it so that we already kind of have all these properties that we're talking about, like existence and uniqueness of solutions. The reason for this is that unlike in the linear systems where with very fairly minimal assumptions, you can just sort of get all the existence, uniqueness, etc. For nonlinear systems, as we're seeing, that doesn't necessarily come automatically, and we have to say more. And so it's good mathematical practice to always say the assumptions that you're making, or else if we didn't say these in our papers, then people could say, well, how do you know that solution of that differential equation even exists and is unique, so then therefore all your proof results can't really hold if you don't have these. So we have to make the requirements that will allow us to do our proofs. So that's why people will see this. W here means disturbance. What else did I need to say about this? Oh yeah, and usually in our papers we use something that we're going to learn today to say that these solutions exist for all time. And so that also is part of what goes on. So here we are. And I think this is a good example to clarify a bit about Lipschitz continuity, even though it's pretty simple. So this is an example. What we're going to clarify is several things. We're going to clarify a bit. Oh my goodness, I just have to say, this is so exciting to learn something about math. So I'm like, okay, we're gonna read this math book. Oh my goodness, it is so amazing to go back now after like seeing so many more things and see how the definitions of derivatives and the definitions of integrals at the time when I learned this the first time, I didn't realize what was going on. I think I thought like people, you know how all math until basically now when we're starting to do this, basically people teach you it as like, solve this problem, here is the way to solve. And how it's not like all this abstract, like if you can find something that looks like this. But then it was so fascinating looking back at all the old math and realizing like, oh my goodness, when it says like integral of f of x dx, it was saying all these things, like it was saying like, oh, this is really the limit of this infinite sum, and don't think of, these are just notation that's signifying like the infinite sum and whatever. This is like mind-blowing that everything has always been the same framework since we started calculus as what we're learning now. And then even that they figured out ways to make proofs of like certain things like, oh, the integral of like x squared is this. And then they just put it in a table, and you know how then it seems like, oh, well, this is math, this table. But then it's not really it came from the fundamental definition, just like everything we're doing. So excited! Okay, anyways. Exciting stuff. So, this is like a whole new world of math, being like, even calculus was the same as what we're doing here. Okay. So, clarify a bit about Lipschitz continuity. So this will only do it, it won't really, because it's clarifying it in the sense that it really has this strong mathematical definition where you would have to really go from that first principles definition and prove anything is locally Lipschitz. And like in multiple dimensions, it can be hard to visualize what that means, but we're going to clarify it a little bit with a 1D example to give a little bit of intuition. The other thing that we're going to do is I think it clarifies a bit notions of sufficiency and necessity. So if we look at this, we say at x is 0, x to the 1/3 is continuous. So if we think back to last time, we had said that there was assumptions related, that if you have, if the right-hand side of your differential equation is continuous on a domain that includes your initial condition, then there exists a solution not necessarily unique for a certain time that's not necessarily long. So what continuity at our initial condition does, and continuity at the initial condition and in some range around the initial condition, is it tells us that there exists a solution, so not necessarily unique, at least one, for some time, but it may be small. So then if we start checking the Lipschitz condition for this, here I'm going to apply it. So it's that f, the difference in two values of the function at two different points in some domain that you're considering is less than or equal to L times x minus y. So this is the condition that would have to hold. So this would have to hold for us to prove uniqueness. And we would have to kind of know some domain of x and y that we're looking at. Here, maybe we would consider like all of R to the n or something. But even if you don't, even if you consider some subset of R, since we only have a one-dimensional system. But even if you just consider some range around x of 0 is 0, so maybe like between -1 and 1 or something, like some region around the initial condition. And then you look at this, so here we have scalars. So the norms might be an absolute value. And if they're an absolute value, that means that we can divide both sides like this. So if we're going to say, okay, I want this to hold for any x and y around 0. So then we could start looking at, okay, what if y was 0? So here's just an example over x is less than or equal to L. So what this would say is that we need x to the negative 2/3 essentially to be less than or equal to L. But then as x is approaching 0, then this is approaching infinity, so it's not less than or equal to L. So then you can see in this case that this thing is not Lipschitz continuous on the right-hand side around 0, which is the initial condition. And then, so this helps clarify a little bit about Lipschitz continuity, because what it helps you see in like one dimension how if you go back and you say what's the derivative of this, for example, it's x 1/3 x to the negative 2/3. So this derivative is unbounded at the origin, and also we have this problem that similarly we can see how this is kind of related to change in f over change in x in some sense. It does have these absolute values, but going back to the definitions of derivatives, this does kind of indicate in some manner how the Lipschitz continuity is related to the well-behaved derivatives, bounded derivatives in some sense. And so in this case, the derivative is unbounded. We saw that it was not locally Lipschitz. And then, so that gives a little bit of intuition about what are we saying about Lipschitz continuity. It's essentially something about well-behaved, like good behavior related to essentially like derivatives. And then also to clarify though from this, sufficiency and necessity. So the reason that, or the theorems that we've said so far have said if the right-hand side has the following behavior, then you can prove that you have a solution that's unique. So here we have a solution. It turns out it's not unique. This is not Lipschitz continuous. So but this theorem, the theorem that we've talked about, did not say that if it is not Lipschitz continuous, therefore there is not a unique solution. So even though that happened in this case, where it turns out there's like 2 solutions to this problem with the same initial condition, even though it turned out in this case that there was not a unique solution and it was not locally Lipschitz, that's not necessarily how it works. What the theorem is, the theorem goes the other way. So it says if it's locally Lipschitz, then you have a unique solution. It doesn't go if and only if. So this is the idea about sufficiency and necessity. Like this is the theorem is a sufficient condition where it says if this happens, then this happens. But it's not necessary. It doesn't say that the result only happens if the first thing holds. So if and only if requires necessary and sufficient conditions, but you can have conditions that aren't that are just sufficient and aren't necessary. And that's a lot of times what we get in control. And so in some sense, you could say that that's conservative, meaning that I'm able to make proofs when certain conditions hold. It's possible that other conditions could hold and the same result would still follow, but I'm not speaking to those. So you could say that's a little bit conservative in the sense that if you apply that, then maybe you require a lot of restrictions that for some cases you might not need in order to get that same result, but you require those same conditions to say like, with these conditions, I guarantee a certain result. Is this okay? Okay, cool. So, then the next thing, so let's talk a little bit about something that would be So then there's the idea of like global Lipschitz continuity. So does something have the same L bounding the, so it's f of x minus f of y is less than or equal to L of x minus y. So one question, as we mentioned last time, you can talk about local Lipschitz continuity, where maybe this can hold in sub-intervals. Mm-hmm. And we gave this example of x squared and said like, well, I cannot bound this function with a line everywhere, but in any sub-interval, I could find a line that's bounding all these functions. But then the question might come, well, are there any functions where you could globally bound with a line and where it would be globally Lipschitz continuous? There are, but it's not that common. So you could say something like this. So this is sat of x. So it's saturating a function y equals x. So this is a line until it gets saturated. And you might wonder, like, why would anything ever get saturated? That would be things like if your actuators, like you could have something like sat of u. So imagine that this is your actuator, and so somehow your actuator's behavior is such that you can vary it between these values, and then it has to, then once it hits a certain value, like the valve won't open anymore or whatever, and then so it saturates. Then another function that's globally Lipschitz would be like just a straight up line, stuff like that. But as you can see, this is pretty restrictive to bound a function everywhere by the same line, so there's not really that many that I can easily think of. But then, but this does lead us to some thinking about, this leads us to some properties of global. So now we're going to look at global existence and uniqueness of solutions. So, in this case, we want to know, can I get that solution to hold for a long time? Well, so I can find, with the Lipschitz continuity, I can get it to be unique for some time, but can I get it to be for all time? So here is one way. So, again, we have dx dt equals f of tx. X of t0 equals x0, and suppose f of tx is piecewise continuous in t, and it satisfies that there exists L greater than 0 such that f of tx minus f of ty is less than or equal to L of x minus y for all xy contained in R to the n and all t contained in t0 to t1. So this is everywhere in all of R to the n, you have the same Lipschitz constant, so it's globally Lipschitz. So so here's our differential equation 1. Then 1 has a unique solution over t0 to t1. So this says that if I can get some very restrictive conditions, where I can get global Lipschitz continuity, then I could get a unique solution for potentially a long time. But that's not that helpful, because it's still very restrictive.
It's globally in this interval.
It means, so this is globally because it's for all R to the n, but in terms of t, it would be in whatever t range where you could have this upper bound t1 be as large as I guess where f of tx, where you're considering it and where it's defined.
Okay.
So this could be large, and then so whatever interval you are looking at this f of tx satisfying these properties, that's the same interval over which you get the unique solution. And so that's different than what we had like last week, where you could have a solution that goes for some time, or you could have a differential equation over some interval, but then you could only guarantee that the solution exists for a short time, potentially, or you didn't know exactly how long. Some time, but it might be small.
Mm-hmm.
So then now we're going to introduce a much more useful result for our purposes, even though it seems more abstract and like it would be less useful. So this next one also can guarantee the solution exists alone. I should also go through the reason why that one works really quickly, and then we'll do a similar reason for why this next one works. The reason that one works is because it's like repeated application of the prior theorem. So you say, oh, okay, this has local Lipschitz continuity, or it has global Lipschitz continuity. So of course it has Lipschitz continuity in some subinterval of r to the n. So then you say, oh, okay, so what I'm going to do, I'm going to have Lipschitz continuity in the interval that I'm in, starting from my initial condition. I have a time range, and then so I say, okay, so that means I have a solution that exists and is unique for some amount of time. And then, so that small amount of time can pass, and then you say, okay, let me check. Am I still having the conditions that I still am in a range where I have a Lipschitz constant, and I have, I'm still in a range of a space where I have the Lipschitz property holds. And you say, oh, yes, so that means the solution, again, exists and is unique for some time. Oh, okay, move forward in time. And then so because it's an r to the n, you never like leave the range where Lipschitz continuity holds. So in terms of, in the time that we wrote the other theorem about when do you get a unique solution, the requirements were that you have this f is piecewise continuous in t, and Lipschitz in x on some time interval in some like norm ball around your initial condition. And then you have a unique solution that's defined for some time. So in that case, you had to have the same Lipschitz constant in your whole norm ball. So then in this case, so it's possible that like so those conditions just say that for some time and in some norm ball you have to have the same Lipschitz condition, then your solution exists and is unique for some amount of time. But then it's you don't really know like where does the solution go from there. Could it go out of the region where you have a Lipschitz constant or something like so? But here what we're saying is, okay, well, I know that every time that I integrate forward that I have a solution, so I have a solution for some amount of time. Now when I get to this new time, I can still have a norm ball where I have the same Lipschitz constant because I'm globally Lipschitz. So always I can reoccur these properties forever and ever and ever. And then that means that therefore, or for as long as the original one is defined time-wise. So that means that I could keep saying, like, keep reapplying this theorem, and then that means that I can keep extending the time. Does this make sense? Okay. Okay, cool. So now the better theorem, which is also going to be similarly coming from the same idea. If f is locally Lipschitz on d contained in r to the n, so we have the same Lipschitz constant within some set, and pick W as a compact set. People remember what compact means?
Closed and bounded.
Exactly. And W is contained within this set D. So it's either a strict subset or could include D. D could, in general, be bigger than W.
Mm-hmm.
suppose every solution of x dot equals f of x of 0 equals x0, remains in W. Then there is a unique solution defined for all t greater than or equal to 0. So here the requirement is only local Lipschitz continuity, so you only have to be able to get the same L's on like subsets of D. So that's way more applicable. And then if you can prove that every solution remains in a set where where the right-hand side is locally Lipschitz, then you can prove that there's a unique solution for all time. And so I think the first thing to address is this seems really inapplicable to say, like, can you find this set where the solution stays there for all times? But yes, you can, and you can do that with some Lyapunov theory stuff, which is the stability stuff that is basically what people use for nonlinear systems, which won't make sense until we do several more lectures. But I guess the basic thing to say is this is not an impossible condition to, without solving a differential equation, know that its solutions remain in a certain region. Even though that's pretty amazing, without solving a differential equation to know where the solutions stay, that's pretty cool. But it is possible to prove that for some systems. But then, so let's talk about why this is again. So the idea is similar to what we just had said. Like, so if I am, here's my region D, say here's some region W that I take, some subset of D, because it could in general be smaller. So in this region, F is locally Lipschitz, and here is some set W where the solution happens to stay. So it also holds that the right-hand side of the differential equation is locally Lipschitz in this region. So I start somewhere. Then, so if F is locally Lipschitz. So it means that I could say, like, okay, well, there is some ball around this initial condition where the solution exists and is unique for a short time. So there, my solution moved there for a short time. Then now you look here and you say, okay, I get some ball where the solution is Lipschitz with the same constant L, because I can just take some ball, and then I moves over here for a short time. Oh, but then now here, still true, because the solutions always stay in this region W where F is locally Lipschitz. So you never run into a condition where, like, oh, well, now I got to a place where somehow Lipschitz continuity no longer holds for this function, so then I can't apply the result anymore. You can always apply the result about Lipschitz continuity, so then you can just keep extending and extending and extending. And then what that effectively means is that, like, no matter where this function goes, you can prove again that because the solution always remains in W, then that must mean that it exists and is unique again for a short time, and exists and is unique again for a short time. So eventually it exists and is unique for all time.
Can you give an example of an F that is not locally Lipschitz?
Yeah, so one example is the x to the 1/3.
Oh, I think I have here, but I forgot.
Oh, no worries. That's just the one from the beginning where we said that, like...
Oh, here.
Yeah.
This is not locally Lipschitz. It's not like Lipschitz at all.
It's not... Oh, okay. Not locally Lipschitz. That's a good question. It is not Lipschitz at the origin, I guess.
Okay, just in 0.
So then, yeah, so I guess the Lipschitz condition doesn't seem to hold in a region around the origin. So then that would be, I guess, what's causing the problem there. So it could still be Lipschitz away from the origin a little bit, or locally Lipschitz away from the origin. But then if you include the points that are problematic, then that's when you would run into trouble.
Okay.
Does that help?
Yes. Thank
you. So then, now one other cool thing. So something that describe. So PID control is very different from model-based control. In PID control, what you do is you get these control laws, and then it's basically like you barely use the model. You might use the model in controller tuning with like a guess and check, like, let me try this tuning and simulate my system and see how that acts. But it's not model-based. And maybe you use those like Cohen-Kuhn tuning rules or whatever to try to start with your model and say like, well, if my model first order plus dead time and then all these things, then I take parameters of my model and say like, here's approximately where I'm going to start with my PID control law. Not saying that this is great, just saying it gives me a starting point. Did people learn all these kind of the controller? So we work on something called model predictive, a really advanced control design that solves an optimization problem to determine optimal ways of operating your system. Really intelligent, this controller, because it solves an optimization problem and it determines what is the optimal way to operate this process now, given how it's going to act in the future based on my model. So you make predictions with a model to predict the future and then say like, okay, if that's how it's going to act, then the best thing for me to do now is the following. Then you apply your control action. Does this make sense? Incorporates a model to make these predictions of how the state will act in the future given the measurement of where it is now. And then, yeah, so then so then that's partly why, oh yeah, so if you have your model, so your model that you're using in your controller is different from the actual process. So the controller will predict something's going to happen, but that's not exactly what's going to happen under those same inputs. So it is good to have this continuous dependence on initial conditions or whatever, because then, so you make a measurement of the state, and then both the model and the controller and the real process are evolving based, like, from that initial state, because we assume that's perfect, even though you can do other things that we can do in control theory, like say, well, what if there was sensor noise and all these things that make it so it's not perfect, but assume it's perfect. So now both cases you have the same initial condition, and you want to know if my model is slightly off, or like how much can it be off, so that the solutions are still similar. Or else imagine the case where you have the same, where like you were to use the same initial conditions, or even slightly different. Say that you had slightly different initial conditions, like maybe a little bit of time passes before you apply the control action or something. For some reason or you have an imperfect measurement. For some reason your initial conditions are different, or your models are different. So that's about like continuous dependence on parameters in some sense. So like you slightly have the wrong parameters in your model. Then imagine how confusing it is if your controller predicts one thing and is completely different from what the system does, even though there's only slight difference in either the model or the state measurement or something. Then that's like, you cannot even work then with control, basically, is like what would happen if their models were that bad, like, or if that was the property of the models, that they were completely different. Well, then we know that that's not really how physical systems act, because we're able to predict things pretty well, even though our models are not usually perfect. So then this idea of continuous dependence on initial conditions or continuous dependence on parameters is a nice thing to be able to talk about. But then, so the problem that the people had mentioned dependence on initial conditions and parameters. Wait, did I write this already? I feel like I wrote this in many
I think
ways.
you have already wrote this, but
So let y of t. Wait, where is this theorem? Where did I write this? Oh, no. Where did I write this? Oh, here. I wrote it here. Oh. Okay. Let f of tx be piecewise continuous in t, and Lipschitz in x on t0, t1 cross w with a Lipschitz constant L where w contained in R to the n is an open connected set. I don't have a great definition of connected here, except that it would be like, this is not connected. This set is not connected. They didn't connect. So, let y of t and z of t be solutions of y dot equals f of ty, y of t0 equals y0, and z dot equals f of tz plus g of tz, with z of t0 equals z0, such that y of t, z of t are contained in W for all t contained in t0 to t1. Suppose, oh no, we're gonna run out of room. Suppose that this g of tx norm is less than or equal to mu for all t x contained in t0, t1, cross w, oh no, for some mu greater than 0. I really need to write this on one board or else it's too confusing. So I'm going to erase this and I'm going to try to get to my maximum height to write it above. So then, y of t minus z of t is less than or equal to y0 minus z0 exp of L of t minus t0 plus mu over L exp of L of t minus t0 minus 1 for all t contained in t0 to t1. And then we'll talk about this in a minute after everyone writes. All right. So, what we can see here is we get the Lipschitz condition with the same Lipschitz constant L in this region W. And then, so that's the requirements on the system. And the way all these requirements come about is through the proofs. Like if you, a lot of times, until you start really proving stuff, it might not make as much sense, like why did they put so many restrictions, but you'll see when you start doing proofs that that's where everything comes from, is like you have to put in your assumptions whatever it takes to get the proof to work. So then here what it's saying is, say that I have, essentially think of this like what we were discussing earlier. I have my one model that you could think of this like, oh, the one the controller's using or something. And here's the other model. Oh, maybe this is like the one the system really has or something. But notice also how these are structured, that this doesn't make any claims about like, okay, for any model you can think of, it has to take these very specific forms. So a lot of times that will be a limitation in the proofs that we are going to be able to do, is that we're not going to be able to prove something for every single case. Like, no matter how off your model is, you can always get a good control or something like that. It'll be like very specific things that but what they imply is something a little bigger that's helpful. So this says that imagine that both of them have these initial conditions that are slightly different. So slightly different models by some amount, slightly different initial conditions. We have to say slightly different in what sense? Slightly different in the sense that the magnitude or the norm of this function for all of the times and states that we're considering that these functions are evolving for is less than an upper bound. And then also that the, so then that means that the norm of the difference in the two solutions is bounded by something related to the difference, how off the initial conditions are, how long you let the system run, and the Lipschitz constant, but then also this mu, which is how big this this sort of perturbation is. So what this is saying is that under certain conditions, you can prove that essentially the difference in the solutions of two differential equations that are off from each other by a little bit and have their initial conditions off by a little bit is bounded by how far off those initial conditions are, and also how far off those equations are, and how long you let the system run. And so clearly if you let the system run longer, so you can see kind of qualitatively, if I have a greater difference in initial conditions, the solutions can be more different from each other, because now there's a greater upper bound. If I have a greater amount of time that I let them run, again, the solutions can be more different from each other. If I have a greater value of this mu, so a greater perturbation, again, the solutions can be more different from each other. So if those things are really tight, if the model is almost perfect, if your initial conditions are almost exactly the same, and you run it for a short time, you can see like the solutions will be almost identical and stuff like that. So this is something that I think this is also a great skill when dealing with nonlinear systems, to be able to analyze things that seem kind of like, so what? What is this? Like, that's how it kind of feels when you first read it. What is that? But then when you break it down and try to say, what is this telling me? Then like what we just said, like if this is bigger, this happens. If this happens, this happens. So even though it tells you something that seems really abstract and like not helpful at all, but then when you break it down, you can pull out of it important stuff. And that's actually true in all of the Lyapunov-based model predictive control stability proofs. There's all this stuff in there where it's like, if the following functions hold, and then like these functions that's like rho plus some function of alpha times it, like all these things, but it's like, what's that even trying to tell me? And then what it's telling you though is like basically, your sampling period, like the following properties of your controller enter disturbances have to be sufficiently small in some way that they're related to each other. So they have to like trade off being sufficiently. So analyzing those things is like a good skill to develop, because it'll be something that's going to come up in basically all of the nonlinear systems literature. So now we're going to do stability and equilibrium for nonlinear systems. So now, okay, so super awesome. We have just covered important properties of nonlinear systems, and of course, by no means is that everything anyone's ever proved about them. There's more proofs in the book about other properties and stuff like that, but I think that gives a good introduction to saying, like, there are a lot of things that we think about in nonlinear systems where you do require certain assumptions to hold. We make those assumptions, and then we use those in proving different stuff. And then, so just like, so that's like almost, if you relate this back to undergrad control, then you would say, that's like the part that we never talk about in undergrad control, everything that we just said, because that's the part that we like take for granted, that there is a solution and it's unique for my linear system. So you can think of that as like the part that we never discuss in undergrad control. Now we're getting to the part that's probably where you first start discussing in undergrad control, which is stability and equilibrium. So essentially dynamics. So you can, as you know, whenever we start undergrad control, we always talk about dynamics before we talk about control. And we have to do the same thing here. The reason is that if you don't understand what you're dealing with, then it's really hard to figure out what you want it to do. And control is about making something do what you want. And so if you don't know what it does on its own, then you don't know what to make it do. So right now, it turns out that stability for nonlinear systems is super fascinating. And we're going to, so first thing, everyone can remember that here we have this autonomous system. So we're going to focus on this right now. So we were talking about f of t and x. Now we're going to talk about f of x. So assume that there's no explicit dependence on the right-hand side. Also, I should say, almost every chemical process model is a function only of x, and then has a continuously differentiable right-hand side. When something's continuously differentiable, it's locally Lipschitz. So basically, like we always get this in chemical engineering. So here, F maps from some domain to R. Suppose x equals 0 is an equilibrium. Point of x dot equals f of x. So something to talk about now. So this means that f, oh, sorry, that was the wrong spot for that. So f of x bar is 0. So that's definition of what it means to have an equilibrium is that the differential equation, there's no time derivatives. Time derivatives equal 0. Definition of equilibrium. So now an important thing to note is that we're going to start talking all over the place now about having equilibria at 0. It's important to recognize, just like you do in undergrad control where you do deviation variables, that you can transform. When you have a system that does not depend explicitly on time, you can always transform your equilibrium and your differential equation. You can always transform your differential equation so that 0 is an equilibrium. So let's just review this because everything I'm going to talk about is going to talk about 0 being the equilibrium. As we've said before, nonlinear systems can have multiple isolated equilibria. Not every one of these is 0, but you can translate every one of these to be at the 0 of a new differential equation. So that's why all of the stability results accounting for x equals 0 can hold for any of these. Does this make sense? Okay. So I'm going to just remind people of deviation variables. So here y equals x minus x bar. So this is my new deviation variable. Here I'm going to say x bar is a steady state. So in this case, maybe it's not 0. 0 could be one of them, maybe. What if it's not 0? I'm still going to call it x bar here for a minute. So then what I can do is I can say, okay, so y dot is equal to x dot. Is equal to f of x, where since we have this equation for x dot. But then we can plug in, for x here, we can plug in the y plus x bar based on this. So now we transform our equation so that now it's a function. So now our differential equation is now y dot equals f of, essentially, you can think of it as f of y, because the fact that there's an x bar, which is a constant in the right-hand side, means that we didn't add, that this is not like making itself a new state. This is just, it's a function of this state, y, but this differential equation is now different than, so I guess I should call this is going to equal f bar of y, because this differential equation will be different. So it'll be something like x dot equals x minus 2. Let me just write this really easy stuff. So then the equilibrium here is that x is 2. So then if I do x, so I'm going to say, oh, okay, so this right now is f of x. So then I can say, okay, deviation variables, y is x minus 2. So that means y dot equals x dot equals x minus 2, but I'm going to plug in, for x, I'm going to plug in y plus 2 minus 2. So I get y dot equals y. Clearly, this differential equation here, f of y, is a different differential equation, or is a different right-hand side than f of x, which is x minus 2. These two are different, but that's fine, because one of them's in deviation variable form, so you could just transform back if you wanted, because then you could plug in, you could say, oh, okay, now I want it back in terms of x, so then you could plug in, for every time you see y, you can plug in x minus 2 and re-get your original differential equation. The difference is this one has an equilibrium at 2, this one has an equilibrium at y equals 0. Does this make sense? It's okay? Okay, cool. So deviation variables are essentially also very important for nonlinear systems, just like they are for linear systems that you learn about in undergrad control. Everything's okay? No question?
What does the dot indicate above y dot?
Derivative.
Oh, it's dy over,
Yeah.
I guess here we have
It's just notation.
dy dt, I guess.
Mm-hmm.
It depends on what the independent variable is. I think we have time here. We'll assume y is a function of time. Good question. Any other things? Is that right? Does that satisfy you, Kim? Sorry? Okay. Excellent. Then, so that is the first step to make sure that we can do deviation variables. That people see how you would do that. So then now we're going to talk only about stability of x equals 0, even though that means stability of any equilibrium point for the system x dot equals f of x, where you can translate it to be at 0. And then you would analyze equilibrium with respect to your new differential equation once you translate it. So the equilibrium point x equals 0 of x dot equals f of x is, so now we're going to start requiring new thinking compared to everything like you ever thought based on undergrad control. So here's the concept. So I'm going to write a definition of stability. Before I write this, I'll clarify it's an epsilon delta definition, so it's an abstract notation definition. And what it's going, so it's not dependent on the eigenvalues or the poles or anything like that. It's going to be dependent on kind of theoretical and mathematical things. And in addition, it's not the way you think of stability. So you think of stability probably now as meaning that the closed loop state goes to the, we're not talking about control. The state goes to the origin. That's not necessarily what stable means here. So just be aware that the definitions we're going to present for nonlinear systems have very specific meanings, and it's important to understand that these are not exactly related to what you've done before, or else you will think like, okay, why does that not say this? So if for every epsilon greater than 0, there exists delta equals delta as a function of epsilon greater than 0, such that the initial condition is bounded by delta. That's what this is saying in a norm sense. The norm of the initial condition is less than delta. This implies that x of t is less than epsilon for all t is greater than or equal to 0. So this is epsilon delta stability definitions. And then let me explain it a little bit once people have it written. You can think of this one as I start close, I stay close. And I'll show why. But it doesn't say I go to the origin. And I'll demonstrate this in a second. So the idea is, so pretend that I say here is epsilon. So someone tells me I want my solution to remain within this amount epsilon. Pretend this is representing like some norm, some like the region of space where this is satisfied. So essentially think of this as a set. In like the set of all states in state space where the norm of the state is less than epsilon. So if you think of that, what this question is saying, I want the actual state, starting from a certain initial condition, to remain within that set. The set of all the states where the norm, in some norm, is less than epsilon. So say that this is that set, and here is epsilon. So we want the state to stay in here. So someone says, I want the state in there, and it can be arbitrarily small epsilon. And then you say, so for every one of them that I imagine, so small, so big, anyone I imagine, then there exists some region where if I start my initial condition such that the norm is less than this delta, so say that maybe here, so here's delta, maybe. So say this is the region of initial conditions where if I start my state here, then it stays within epsilon. So it doesn't necessarily go to the origin, but it stays in there. So that's sort of what I mean when I say start close, stay close. So you start in some region, and then you stay within another region. And this has to hold no matter how big or small epsilon is. So, yeah, so the idea is saying, say epsilon is super tiny, then I can always find some set of initial conditions where if I start in there, the state remains even in that tiny region, epsilon. And then if I make epsilon bigger, now I can find some set of initial conditions where still the state is maintained within that region. And so that's the idea of stability. So we would say that if it is true that the nonlinear system's behavior is such that when you start from those initial conditions, the way it evolves causes the closed-loop state to behave like that from certain sets of initial conditions. Like, so when you start in these ones, they stay in that. You make epsilon bigger, you can still find some initial conditions that stays in there. Then this means that that equilibrium point, and remember we talk about equilibrium points, not about systems, because systems can have multiple equilibria. Talking about the specific equilibrium point, that point is stable in the epsilon delta sense, which is essentially I start close, I stay close, not necessarily go to the origin. Is this okay?
It's the same idea as bounded inputs, bounded outputs. It's different, I guess.
This has no inputs.
But it's just the similar idea again. You have a bounded initial condition, so you stay bounded in this set of states.
I'm hesitant because I don't have a definition right now of exactly what bounded input, bounded output means mathematically. Okay. So I'm hesitant to say like yes or no to that.
Just trying to do an analogy, but I think start close, stay close is better in this case. Mm-hmm.
Yeah, it's probably easier because there is no input here, so it probably like kind of gets a little confusing. Mm-hmm. Then, so we can also talk about. So this is local. I should clarify this is local stability.
Okay.
We can also talk about global. So what it means by local is just imagine that I have multiple equilibria, for example. I have one here, one here, one here. Clearly, say that one of these is, so clearly if I start here, I'm not going to the origin. There's this other equilibrium. So when we say local, though, we mean like it's possible that, say this one is stable, but it's possible that the states like starting here start going to this one or something. Say they do. I don't know. I'm making something up. Well, but if you're here, then that doesn't mean this one couldn't be stable, but maybe there's two that are stable and maybe this one's unstable. It's like, oh, they're all going here. I don't know. I'm making something up. But this one could still be stable even if, and this thing still holds because then say that you say, I want my epsilon really big, and then they say, but the requirement is that for any epsilon, so you want your state to remain within now this epsilon. That includes all these other things. And then you say, can I find a set of initial conditions such that x of t is in epsilon for LT? And then like, well, yes, like I could still choose a small delta here, and then the state still remains, clearly it's in epsilon. So like it's still possible to satisfy this definition. It doesn't mean that I have to like be able to guarantee that like all the, yeah, so this is local stability, I guess, is the outcome of this, is that you are talking about whether or not there exist some initial conditions, they don't have to be super big, where you always stay in epsilon. So it has to hold for some amount. Is this okay? Doesn't have to hold it globally. We can talk about what would be the definition if it had to be globally stable. So here we can say global stability So one thing that has to be true about global stability is that one, it has to be the equilibrium point. Now, so if we want to say an equilibrium point is globally stable, it has to be stable in the epsilon delta sense. So that whole definition has to hold. And then also, we have to add another condition, which is a boundedness condition. So this says that, so a boundedness condition has to hold. Where for all delta hat, so this is different than the other delta, some new delta, just going to call it delta hat. This is not, so there's epsilon delta has to hold here in the sense that we already defined, so that has to hold. Now we're going to say, and another property that I'm going to similarly define with like something less than some norm. I'm going to use a different notation. It looks the same, but remember this is different. This is boundedness, the other thing is stability. So there exists epsilon hat equals epsilon hat of delta hat greater than 0, such that x of 0 is less than delta hat, means x of t is less than epsilon hat for all t greater than or equal to 0. So notice the differences. Oh, sorry, I'll let people finish writing first, and then I'll clarify. So it's important to notice the differences between the first, so stability versus boundedness. So when we talked about stability, you know how we just said, like, okay, we were talking about local stability. So we said, tell me epsilon, how close you want me to stay within, or I guess within what range of states you want the state to stay. And then I'll find you a set of initial conditions where I can guarantee it stays in there. I didn't say it has to stay, I didn't say it has to go out as far as epsilon. I just said it has to stay in epsilon. Notice that here, so that would be local stability. So it's possible that like out here, the state starts going to infinity, for example, and goes off and becomes unbounded. And that's fine because I can still find a set of initial conditions around here, even if I made epsilon this big, where, so maybe I start here, the state will go to infinity. It's not bounded, but I can find a set of initial conditions where I maintain within this epsilon, because then I would say, well, let me choose a smaller ones that don't include that. So from a stability standpoint, I still have local stability, so that's fine. But then if I go here to boundedness, now I have something different, because now I say, okay, now I'm requiring that no matter how small or big I make my initial condition, the state is maintained within some region. So this means that I cannot have unboundedness like this. So now it says, say that I say, make my initial conditions out here. So now that kind of flipped. So now this is like delta hat. It says, make my initial condition here. Now, what happens with, now what happens to the state? Does the state say bounded if I take an initial condition in this range? And the answer is no. In this case, so then you would say, okay, well, then this is not global stability of this equilibrium point. The state out here is going somewhere else. But then, but say that it stays in here or something, or it stays within epsilon, now I'm good. So can you see the difference between stability and boundedness in this case? It's okay? Are you sure, Dominic?
I think it's very hard then to have a global stability. You have multiple equilibrium points. One of them could be, I think if one of them is, for example, saddle point or an unstable node, I think we not have a global stability at all, right?
think it's a little hard to say, because then you know how there can also be things... I don't have a clear answer for that, because you know how there can actually be stable, like, orbits?
Right.
So it's hard for me to make a general claim. I'm not sure if I feel confident to make any general claims.
Can we have a global stability? Oh, that's
Well, like, I think linear systems are a great example of global stability. So you start anywhere, you go to the origin, that satisfies all of the conditions, even though it goes to the origin. There was nothing here saying it's not allowed to go to the origin. It's just I said it doesn't have to. So linear system is a great example of global stability. Happens to be global asymptotic stability, so it even satisfies, actually even global exponential. But it satisfies some additional properties, but this would be one example.
But this is because you have one equilibrium point. If you have a multiple equilibrium points, can you actually have a global stability?
That's a good question. I don't know about that.
Mm.
I wrote in my notes that you can't, but these notes are from so long ago when I was an undergrad, and I didn't really know what was going on that well when I was an undergrad, so I also might have copied things wrong, because I might have like not known what I was doing. So I think that is a very good question. Someone would have to think through it. I think what you would have to do to prove one way or the other, you would have to be able to demonstrate that if you have more than one equilibrium, one of these conditions cannot hold. I think stability can still hold. So the question is, will boundedness hold if you have more than one equilibrium?
Mm-hmm.
So which condition do you think will get violated here by having more than one equilibrium, Enrique? Let's think about it. So I guess, say I have two, so maybe the question is, can you have two, so if I have two equilibria, if I start here, I stay here.
Mm.
So as far as I can tell, then, if I put my initial condition, if I allow my initial condition to be here, I can still, that seems to be okay from the perspective of, if I start there, I stay there. But then I guess the question is about the stability of the other equilibrium. Will it have to have, like, so if trajectories go to this one and go away from this one, is it possible to have a system where all the trajectories go here?
Yes. I think it's the only way.
I don't know if that's possible. That looks pretty weird.
We have an unstable node and a stable node that is all converged in this equilibrium point.
Wow, I'm not sure.
Yeah, I'm not sure either.
That's interesting. I don't know.
Okay.
And I guess you would also have to prove, though, that they didn't leave. It seems like it would be hard, huh? Because then you would have to also prove that, like, if I start here, that the trajectories don't leave here because they have to remain within the epsilon. Wow. Interesting. Interesting. So then, let's write what instability is. So x equals 0 is unstable. If it's not stable, which then we have to sort of negate the statements. So if there exists epsilon such that for all delta greater than 0, wait, I think I wrote a better one of these. I think it's at this bottom. It is not stable if there exists epsilon greater than 0 such that for all delta greater than 0, there exists x of 0 such that x of 0 is less than delta and x of some t is greater than epsilon or equal to epsilon for some t is greater than 0. So this should negate many of the properties about stability. It says that if you have, there's some epsilon such that you can find a delta where if you start your initial condition in there, then eventually the closed loop state exits epsilon.
The previous one is a good example.
Can you phrase this?
Maybe
Make it a little more?
this one here, like, and this could be like stable in epsilon delta sense, but not in the boundedness. So sorry.
Oh, okay. Yeah, so here this is about local instability. So it means that, so we're negating this. So the definition of local stability was that for all epsilon that you tell me you want to stay within, there exists some initial condition where if I set those initial conditions, then my state overall over time will stay within epsilon. So then this says there's some epsilon, because the other one said for all epsilon. So here I'm saying there is some epsilon out of all those ones that you could choose for all, such that no matter what delta I was to choose, even if I made it very small, even if I made it big, then if I start my initial conditions within that set delta, eventually the closed-loop state leaves the region epsilon at some point. So it's saying there is at least one trajectory where there is nothing I can do, or there's at least some condition where there's nothing I can do in the epsilon delta sense to try to prove that, to show that stability holds. Is this okay? Any questions? Okay. Now we're going to talk about converging to an equilibrium. So this is more in the sense people know about. So convergence to equilibrium.
Just to clarify, this is we are discussing here stability related to a specific equilibrium point. We cannot say that it's stable, the system is stable, for example.
Yeah, exactly. We cannot say anything.
It's specifically for equilibrium point.
Yeah. Because when we talk about stability of equilibrium points, what we're really wondering, when we talk about stability for any system, what we're wondering is, if I start my initial condition off of that equilibrium, what's going to happen? So we're always concerned about an equilibrium, even when we talk about global stability, even when you talk about linear systems, and you have, what time is it? Okay. When you talk about linear systems even, and you know how when you would say in linear systems, when you use that terminology, the system is stable. What you really were trying to say is whether or not the closed loop state would go, or whether or not even with no closed loop, no inputs, whether or not the state, when you start off the steady state, goes to the origin. So the question has always been about that origin, because the origin is always the focus. It's about, do the states, if I start off that origin, go to that origin, or whatever. So we always...
This coincide, right?
Sorry?
For linear systems, this coincide, this concept. The system being stable and the equilibrium point being stable.
Yeah, so we don't actually use, that's why even in linear systems, it's really bad terminology to talk about stability of the system, because it just sets everyone up for confusion. Like, what does that even mean?
I'm asking this because I learned in undergrad that we also call it stable system or unstable system, but actually the appropriate term would be stable on equilibrium point or unstable.
Yeah, that's exactly true. I think everyone learns in undergrad the stable system or the unstable system, but even if you think about a real chemical process, like, I think almost, like, chemical processes really have nonlinear dynamics. They don't really have linear. So even then, it, like, doesn't really make sense to ever talk about stability of a system, because it's really nonlinear. Even if you take the linearization, linearizations are, as we learned a few days ago, you know how we said we could look at linearizations and then try to look at eigenvalues of the linearization to try to get some idea of local stability. So even then, even when you take linearizations, you're only looking at local stability, so it still has to be around an equilibrium point. So basically, we will never talk about stability of a system again. Unless people want to ask about it, that's fine. But I just mean, in no paper, if anyone writes in a paper and they write stability of the system, if I catch that, I'm going to say, no, it's stability of the equilibrium.
Okay.
So this is a concept of attractivity. So this is where we start getting to the idea of, so everything we said about stability so far, we said in nonlinear systems, we can define whether or not the state is going to the origin or not going to the origin is still fine. So, like, imagine that your trajectories do something like this, like that for any initial condition that it stays in this orbit. So that's going to meet the epsilon delta definition of stability, but it never went to the origin. But if that's the way that this system behaves, then the origin here is still stable, because for like different initial conditions, you start close, you stay close. So, but that's not really how people have usually thought of it, but this at least gives a little more rigor to like, okay, say it's doing this. Say it didn't go to the origin. So what does that tell me? Okay, well, and also if you think about what we want to do with nonlinear systems, like sometimes it can be just fine to all you want to do is say, like from a safety perspective, imagine a chemical plant. The thing you most care about, the reason you care about stability, is partly because you want things to go to a steady state. But if you didn't care if it went to a steady state, if, for example, it did actually make you more profit if you didn't go to a steady state, you don't actually care if it goes to that steady state then. What you really want is you want to make sure from a safety perspective that the closed-loop state doesn't go crazy. So I think like introducing this concept is kind of helpful to just like in your mind start gearing up for like, you know, I can have stability in new senses. Like I don't have to say stability is only when I go to my steady state. That's not necessarily true. You can think about like stability as being sort of like a property, just like how do the solutions behave? Let's start characterizing ways they could behave. And then that's good. So but now if we want to talk about does it go to the steady state, because a lot of chemical processes have been designed to go to steady state, so people still care about that. So x equals 0 is attractive if there exists delta bar greater than 0. So now a different delta such that if the initial conditions norm is less than delta bar, this implies x of t goes to 0 as t goes to infinity. So this is for all of these x of 0s less than delta bar. We see again this is a local result. It doesn't say for every initial condition that's ever possible, this has to hold. It says there exists some deltas greater than 0, where if you start in there, then the state goes to the origin for all of the initial conditions within that region, where you start within that delta. And then remember that when we write this sort of notation, sometimes I think it's really helpful, like what I was saying earlier about the calculus, and thinking back on like what does the integral notation mean. The reason that I was wondering this and why this was such a breakthrough is because there's a lot of times in proofs in books where they will just like something that like you can't integrate, like a vector function, like something that what does it mean to write the integral of a vector function, like the integral of this f of x, for example, this f of x here. What is that notation trying to say? When I read that, I'm like, I'm so confused. How can you use that in a proof? And then what I realized last night when I was reading this, I was like, oh, that must have some other definition, like that I've forgotten, that's probably related to something about infinite sums in some sense. But I haven't got that far in the multivariable calc yet. I'm still in the single variable part I was reading. But I just thought that's really helpful sometimes to remind yourself, what does notation mean? And so here I think that too, like when it says x of t goes to 0 as t goes to infinity, this should be something about like infinite series, like, oh, as you keep having these series, then like the x of t. So I think sometimes it's helpful just so that, or else it's like, okay, what does that mean again? The interesting notation there. So
this could be any equilibrium point, not necessarily the origin.
Oh yeah, so this is just a definition of what it would mean if you wanted to say you have an equilibrium point and someone says, is that attractive? And then you say, let me check. It will be attractive if the following holds.
Okay.
Yeah, so you just have to evaluate. But we're talking here about x equals 0, but you can translate any equilibrium point to be at x equals 0 by translating your differential equation. And then so you would look at the differential equation that holds around that equilibrium point. Like what I mean is, if you write in deviation variables, you change your right-hand side. So the differential equation, when you look at whether or not its solutions do something, you're looking at the transformed equation.
That's why it's useful to write your differential equation in deviation variable.
It's not really necessary. It depends on what you're doing. If you're doing theory, you have to. Straight up, you have to, because all these results are for when x is 0. So if you need to apply these, you have to. If you're just doing numerical integration, it doesn't actually matter, because numerical integration is based on, is not based on this. But Lyapunov functions also have their zeros at 0, which is why a lot of times in the codes that you see me doing, it's because of those Lyapunov functions that I have written in deviation variable form. Because or else it's really confusing, because the Lyapunov functions we're going to learn about have to have the equilibrium point at 0, because they're like the next step after we talk about definitions. So then the problem is if you don't translate your, if you don't put your model in deviation variable form, then when you get to constraints about Lyapunov functions, then you have to start worrying about like, okay, how do I rewrite this constraint so that it has the 0 at the equilibrium, and then it gets a little more confusing.
Okay.
So, yeah. And you can also say globally attractive. So this is for all, this would have to hold for all initial conditions. So for any initial condition, attractivity holds. Certainly if something is globally attractive, it must be the only equilibrium. Because by definition, anything that is another equilibrium would even stay at its equilibrium. So regardless of stability of any other equilibrium, the definition of an equilibrium is that if you start there, you stay there. So if that's true, then clearly you do not go to the origin from that point. So that would be an initial condition where this would not hold, because you would not go to the origin from another steady state. Because if you start at that other steady state, you stay at that other steady state. So essentially, for global attractivity, you must be the only equilibrium. So x equals 0 must be the only equilibrium. Should I say again?
Why you must have just one equilibrium? Could not have two? Or?
So if it's globally attractive, that means that for any initial condition that you could do, then the closed loop state will go to the origin as t goes to infinity.
Right.
Imagine that then I have this equilibrium and this one. So then if I start here, I will not go here, because this is an equilibrium. So I start here, I stay here. So it's impossible that if there were two equilibrium, that this could be satisfied for all initial conditions. Because even if I only had, even if this was like unstable, say this was unstable and all the solutions went here. Is okay? Sorry, what?
I was going to ask, what if you have like one unstable?
Yes, this is the point.
Yeah, that even if this is unstable, that only holds like for any initial.
Besides that point. Basically.
Yeah, besides that point, but then still this point you don't go. Or still at this point, you have trouble because you will not go to the origin from this point because you start at that point, you stay at that point. That's the definition of an equilibrium. It's okay?
Yes, thank you.
Okay. Everything good? Excellent. Cool. So now we're going to try to start talking about things that are very interesting. So just because something is attractive does not mean it's stable. What? It's crazy. So let's see. So imagine that you have this equilibrium point and that there's something where like it always comes back to it or something. So there exists, so now we're going to talk about local attractivity again. I can start any initial condition I start here. If it does this, it comes back. And eventually I start here, then as t goes to infinity, I go back. Does that part make sense? Just to make sure the logic is flowing. Any initial condition, no matter how small I make this ball, I start in a set around there. The given way this works is it comes back.
But this is not stable in the sense of epsilon.
Yeah, but it's not epsilon delta stable.
Right.
So first, does it make sense that it's attractive according to the attractiveness definition?
Okay.
But then, in terms of the epsilon delta stability definition, if you think of that, remember that that's essentially start close, stay close. No matter how close I start here, if you tell me epsilon is this, no matter how close I start, I can never stay in that epsilon because all my solutions are going to leave and then come back. So it is attractive but not stable in the epsilon delta sense. So Then the question is, okay, so what about those linear systems, those that have those equilibria where the state goes to the origin? That's like attractive and stable, right? So does that have a special name? Yes, it does. That's called asymptotically stable. So asymptotically stable means stable and attractive equilibrium point.
This is the best of the words, right?
Actually, there's an even stronger stability definition too. It's called exponentially stable, which is actually what linear systems are. And that's about like the rate at which it goes to the equilibrium or whatever. But basically, asymptotic stability is the one where you want to go to the steady state. Oh, this is also local. So, of course, you could make it global. We'll talk about that next. So, local asymptotic stability, it meets the epsilon delta definition of stability, and it meets the definition of attractivity in terms of like initial conditions and the deltas and stuff. So all this goes back to fundamental definitions when we say this, but you can sort of intuitively understand this one. We can also talk about global asymptotic stability for an equilibrium point. So it needs to be globally stable and globally attractive. Remember that this means it is the only equilibrium point.
So this global asymptotically stable just holds for linear systems.
Well, there could be other systems that are nonlinear where potentially this could hold. Like, it's not. Actually, this is one of the cool things about control is that with control you can change the dynamics. So, for example, x dot equals negative x. What is it? Cube squared. Let me think, and then let me see. So when this is positive, it's negative. When this, it must be like a cube. Okay, when this is positive, this is negative. When this is negative, this is positive. Okay, that would be the right way. So here you can see that whenever you're at an initial condition below the origin, it pushes you toward the origin because it increases. So x dot is increasing below 0, and it's decreasing above 0. So that means that no matter where you start on the real line, the solutions are going to 0. So this is actually globally asymptotically stable, even though it's nonlinear. So it is possible to have nonlinear systems that meet this definition. And that's one of the really cool things is with with control, what we're going to be able to do for nonlinear systems. Like, so imagine that I have something like this, just to show control is so great. X dot equals x cubed plus u. Okay, so if u is 0, this is not. I think this is unstable. This is an unstable equilibrium if I don't have any input. So if these are my dynamics without an input, this is unstable equilibrium. But what if I have u is equal to negative 2x cubed? So now x dot is equal to negative x cubed. So I'm back now by having an input that I specify in a certain way. I have actually completely changed the way my system behaves, so that even though without having any input, it was an unstable equilibrium. With an input, the same equilibrium has become globally asymptotically stable. Wow, control is so great. Look at that. That is so cool.
Then I think this is another definition for control. We can actually change the poles and the eigenvalues of our system to make it like a global asymptotic stable. So it's very nice to see this.
And to clarify, in a nonlinear system, there are no poles and no eigenvalues, because that holds for linear only.
Right.
But yes, in a linear system, you can do those things. And then, so there's actually, wait, this is about Jacobians? Okay, what goes on about something about the Jacobian? Oh no, there's only 5 more minutes, but we're just getting to awesome control stuff. Okay, yeah, so if you want to find linearizations, you can take Jacobians,
which is that thing that we did in for Newton's method in the thing. Yeah, and that, because that gives you the linear approximation. So what's the other stuff I want to cover? Oh, okay. So now we're going to cover really quickly exponential stability. So exponential stability is another type of something that's exponentially stable is asymptotically stable, but exponential stability describes like a certain rate of decrease. It kind of comes, you know how the solution of x dot equals, say I have x dot equals negative x. So x dot, so dx over negative x, dx over x equals negative dt. And then you say like ln of x is equal to negative t, so e to the negative t is equal to x or whatever. So here, the state, the way it evolves in time is related to an exponential. So we say like imagine you start off the steady state, and then the way that, so x of t is equal to this. So if I start off the steady state, then it's e to the negative t. So, this was for the case that I guess I must have assumed a certain initial condition here. I guess I have assumed some initial condition, which I probably assumed that the initial condition was 0 at 0 or something. But so you could write it out with different initial conditions, but you would get something like this where the state evolving from that initial condition is going to have some exponential rate of decay toward the origin. This is a concept of exponential stability. You can see that that's the way that linear systems, so linear systems are stable and attractive to the origin x equals 0, but they have an exponentially related way in which they're decaying. So this is kind of this notion of why we're going to call this exponential stability. And it has a more precise definition than that, but I guess I'm running out of time. Okay,